video presentation CHM361 Valence bond theory that will submitted to Dr. Fariza Aina binti Abdul Manan. Introducing our group members. First, Ainur Afika, Nur Fahana, Iza Shahira, Nurin Akila and Fatnin Rafana. Let's start our presentation.
What is valence bond theory? Valence bond theory is a model that explains chemical bonding by focusing on the behavior of valence electron, which are the electrons in the outermost shell of an atom. According to VBT, a covalent bond is formed when two atoms share a pair of electrons. This sharing occurs when the atomic orbital of the two atoms overlap in space. When the orbital overlap, the electrons from both atoms occupy a region between the two nuclei. Because the electrons are attracted to positively charged nuclei, the shared electrons are attracted to both atoms at the same time. This lowers the overall energy of the system and creates a stable chemical bond. In this way, valence bond theory explains why atoms come together to form molecules rather than remain separated. Basic principle orbital overlap. The most important concept in valence bond theory is orbital overlap. An atomic orbital represents a region around the nucleus where an electron is most likely to be found. These orbitals have different shapes such as spherical orbital and dumbbell-shaped p orbital. When two atoms approach each other, their orbital may overlap. This overlap creates a region of high electron density between the two nuclei. The positively charged nuclei are attracted to this negatively charged electron cloud, which pull the atom together. The strength of the bond depends on how much the orbitals overlap. A greater overlap produces stronger attraction, resulting in a stronger and shorter bond. Why electron must have opposite spin? Because of a quantum mechanical rule known as a Pauli exclusion principle. This principle states that no two electrons in the same orbital can have the same set of quantum numbers. Since the spin is one of these quantum numbers, the two electrons in the bonding orbital must have opposite spin. When two atoms bond, their overlapping orbitals form a single bonding orbital that holds together electrons. If both electrons had the same spin, they would not be allowed to occupy the same orbital and the bond called not formed. Therefore, opposite spin are essential for the formation of a stable covalent bond.
Next, we go to the sigma bond. So what is a sigma bond? Sigma bond is a covalent bond formed by the head-on, which is end-to-end overlap of atomic orbital. As we can see the figure on this slide, which is sigma overlap, can result from the overlap of s orbital with p orbital. Head-on orbital overlap occurs when orbital overlap directly facing each other. Can involve s orbital, p orbital or hybrid orbital. Produce maximum overlap leading to strong bonding. Next, there have three types of sigma overlap. The first one is SS overlap, overlap between two s orbital, for example is H2 molecules. The next one is SP overlap, overlap between an s orbital and p orbital, such as HF molecule. The last one is PP overlap, overlap between two p orbitals along the same axis, for example single bond in F2 or Cl2. So this is the example of sigma bonds. The first one is H2 formed by SS overlap between two hydrogen, one s orbital. There have one sigma bonds. The second one is HF formed by SP overlap between H, one s and F, two p orbitals. There have one sigma bonds. The last one is CH4, which is methane. Carbon undergoes sp3 hybridization. There have four sigma bonds formed by sp3s overlap between C and H. The shape is tetrahedral. Next, why sigma bond is strong? It is because maximum orbital overlap increase electron density between nuclei, strong electrostatic attraction between shared electrons and nuclei, and then provide high bond strength compared to pi bonds. The last one is allow free rotation around the bond axis.
Next is pi bond. This slide explains what a pi bond is. Definition of a pi bond. A pi bond is a covalent bond formed by the side-by-side overlap of two parallel p orbitals. Formation of pi bond. The electron density of a pi bond is located above and below the internuclear axis. Pi bonds are formed in addition to a sigma bond, so they cannot exist on their own. They are also weaker than sigma bonds because the orbital overlap is less effective. This slide shows the role of pi bonds in multiple bonds, which are double and triple bonds. For the point number 1, double bond. A double bond consists of one sigma bond and one pi bond. For example, ethene, C2H4, has one sigma bond and one pi bond. The carbon atoms are sp2 hybridized. The picture it shows the sigma bond is formed by head-on overlap, while the pi bond is formed by side-by-side overlap. Next, point number 2, triple bond. A triple bond consists of one sigma bond and two pi bonds. For example, ethane, C2H2, has one sigma bond and two pi bond. The carbon atoms are sp hybridized. This is why triple bonds are stronger than double bonds.
So now, I will explain about hybridization. Hybridization is the process where atomic orbitals mix together to form new hybrid orbitals. This happens so that atoms can form stronger bonds and molecules can have stable shapes. Hybridizations occur because electrons repel each other. By mixing orbitals, the hybrid orbitals can spread out evenly, which helps reduce electron repulsion and makes the molecule more stable. The types of hybridization depends on the number of electron domains around the central atoms, and this will determine the molecular geometry. First, the sp hybridization forms a linear shape like in PeH2. Next is sp2 hybridization, give a trigonal planar shape, for example BF3. Then sp3 hybridizations form a tetrahedral shape such as CH4. For larger molecules, sp3d hybridization forms a trigonal bipyramidal shape like BCI3. Lastly, sp3d2 hybridization give an octahedral shape as seen in SF6. So in conclusion, the number of electron domains determines the hybridization, and the hybridization determines the shape of the molecule. Hybridization helps us understand why molecules have different shapes and strong bonds.
Next, I will explain the example shape for CH4, NH3 and H2O. The figure on this slide is Lewis structure for CH4. Carbon contains 4 valence electrons for CH4. That means the number of sigma bond for CH4 is 4 sigma bond. Carbon undergo sp3 hybridizations. For molecular geometry for CH4 is tetrahedral because there are no lone pair for CH4. That means there are no effect for lone pair. On this slide show NH3 Lewis structure. NH3 contain 5 valent electron, 3 of it is hydrogen and leaving 1 lone pair. That means the number of sigma bond for NH3 is 3 sigma bonds. Nitrogen undergoes sp3 hybridizations. The molecule geometry for NH3 is tetrahedral, but due to 1 lone pair, the molecule geometry for NH3 is trigonal pyramidal. Because of their 1 lone pair, repel bonding pair more strongly and reduce bond angle to 107 degrees. The last example is H2O. On this slide, show H2O Lewis structure. Oxygen contains 6 valent electrons. 2 of it is from hydrogen and leaving 2 lone pair. That means the number of sigma bond for H2O is 2 sigma bonds. Oxygen undergo sp3 hybridization, and the molecule geometry for H2O is tetrahedral, but due to lone pair, the molecule geometry for H2O is bent, and their effect for lone pair because of 2 lone pair compress bond angle further to 104.5 degrees.
In conclusion, valence bond theory explains chemical bonding as the overlap of atomic orbital from 2 atoms, where the electrons with opposite spin are shared to form a covalent bond. The theory are successful subscribed bonds formations, bond strength, and bond direction by emphasizing orbital overlap and hybridization. It helps explain molecule shape and localized nature of bond in many molecules. However, valence bond theory has limitations, such as its inability to fully explain magnetic properties and electron decolorization in some molecules. Despite this limitation, PBT remains a fundamental and useful theory for understanding the basic concept of chemical bonding.